Chapter 1, An Introduction to Computers and Problem Solving. So when we talk about a computer programming language, what we're talking about is how we communicate with the computer. So when computers were first being developed, programmers used machine-level language to talk to the computer. Now, machine-level language is a low-level language that's hard for humans to understand, but easy for the machine to understand. So in order to promote programming and allow users to more easily program, we built intermediary devices called compilers. Compilers take a higher level language and convert it to machine level language. Now each programming language has its own compiler. So a high level language such as C++, Java, Visual Basic will each have its own compiler that takes a high level language and converts it to machine level language. For Visual Basic consists of instructions such as click, if, and do, something that we can understand and something that we can use and process. So why Visual Basic and why not one of the other programming languages? Well, Visual Basic is very GUI oriented. GUI stands for Graphical User Interface. So when we use Windows, we're looking at a GUI. Windows has windows, icons, tiles that you click on and manipulate with a mouse and move things around. That's what Visual Basic does. Other programming languages such as C++ are more console driven. They're more command line driven. While it's possible to program GUIs, it takes a lot more work and a lot more effort to get the same program out. So we're going to talk about Visual Basic. We're going to use structures that are found in all programming languages, and we're going to discuss them within a graphical user interface. So now that we know how to talk to computers, how do we get them to do things? So normally when we're going to use a computer, we're going to use it to do something that's complicated, something that we normally wouldn't be able to do by hand without taking multiple steps. So we're going to take those steps, we're going to take those commands, we're going to break them down into instructions that can be expressed within the Visual Basic language. Those sequence of instructions are then called a program. So a program is just simply a sequence of instructions written in whatever programming language you're compiling. Programs can be very short, they can be just a few instructions, or they can be millions of lines of instructions. So we're going to talk about some simple programs here to introduce us to the language. So what do all programs have in common? Well, they take data, they manipulate it to do something, and then they produce a result. So that's 3 steps: input, process, and output. Input comes from files, the keyboard, other input devices like video cameras. And output can go to the monitor, it can go to a printer, or it can go to a file. Now, how does it do that? Well, it does it between a combination of hardware and software. Hardware, of course, is going to be the physical components of our computer, our CPU unit, our disk drives, our monitors, our keyboards. Software is going to be the instructions that tell our computer what to do. So who writes the software? The programmer writes the software. The programmer is the person who solves the problems and writes the instructions for the computer. When the programmer has written these programs, they're going to hand them over to the user. The user is going to be the person who uses the program that's written by the programmer to perform some tasks. Well, we talked about how we're going to write code and how we're going to write our programs for graphical user interfaces. Well, across different versions of Windows, our programs may look different. Vista, Windows 7, Windows 8, they all just have a different look and feel. However, the way that the program operates is going to be the same no matter what. Now we're going to move into our program development lifestyle. How do we build our programs? How do we get them to do what we want? So our book talks about a computer program. Well, a computer program can also be called a project, it can be called an application, it can be called a solution. When we talk about our program development lifestyle, we talk about software referring to a collection of instructions for the computer. And the computer only knows how to do what the programmer tells it to do. Therefore, the computer programmer has to know how to solve the problem themselves before they can tell the computer how to do it. Computers can't solve problems that the user hasn't already solved. So in order to get the computer to perform a task, we need to first determine what we want for output, have to identify anything that we need for the input, and determine the process necessary to turn the input into the output. So we need to problem solve like we would an algebra problem. So how fast is a car traveling if it goes 50 miles in 2 hours? So our output is a number given the speed in miles per hour. Our input is the distance and time that the car has traveled. We know that our process equals speed equals distance divided by time. So if we put this into a pictorial representation of our problem-solving process, we see we start with our input, we do some processing, and then we have our output. So in order to properly plan our program, we got to develop what's similar to a recipe. So our ingredients and amounts are what are determined by what we want to bake. Our ingredients are going to be our input. The way you combine it is called the processing. And then finally what's baked is going to be the output. So when you're sitting down and you're writing code for your programs, you want to make sure you have a plan when you're writing your program. You don't want to just jump in and start writing code automatically. That'll only get you into trouble. The more complicated the problem, the more complex the plan must be. So you want to plan and test way before you start coding. Otherwise, you're going to spend a lot more time coding and rewriting code to get it to do what you want it to do. So then we talk about the program development lifecycle. So the first step is to define the problem. We analyze our problem. The second step is to design the solution. We want to plan what our program's going to do, how it's going to ask for data, what it's going to do with the data that it's been asked for, and then how it's going to display to the user. Then we want to choose our interface. We want to select the objects that we're going to use to get input from the user to tell the user to continue on. Then we're going to code. We're going to translate the algorithm into a computer programming language. We're going to test our code. We're going to debug it. We're going to remove any errors in the program and get it to work correctly. Then we're going to complete the documentation, organize all the materials that describe the program, and present it to the user. So in doing that, there's a number of different tools that we can use. There's 3 tools in particular that are used to convert algorithms into computer programs. The first is a flowchart. A flowchart graphically depicts the logical steps needed to carry out the task and show how the steps relate to each other. We could also use pseudocode. Pseudocode uses English-like phrases with some knowledge of Visual Basic terms to outline the program. The third is a hierarchy chart, which shows how the different parts of the program relate to each other. So we talked before about an algorithm. An algorithm is a step-by-step series of instructions for solving a problem. So a recipe could be an example of an algorithm. So how many stamps should you use when you're mailing a letter? So one rule of thumb is to use 1 stamp for every 5 sheets of paper or fraction thereof. So our algorithm is going to request the number of sheets of paper, call it sheets, and that's going to be our input. We're going to divide the sheets by 5. That's our processing, the part that the computer is going to do. Then we're going to round that quotient up to the next whole number value and call it stamps. Again, that's processing, a step that the computer is going to do. Then we're going to reply with the number of stamps. That's going to be the output. So we're going to use a flowchart, again, to graphically depict the logical steps to carry out a task and show how the steps relate to each other. So when we use a flowchart, there's a number of different symbols that are used. So an arrow is also called a flow line, and that's used to connect the symbols and indicate the flow of the logic. We have our ovals, which are terminals, which is used to represent either the start of the program or the end of the task. We have our quadrilateral, which is an input and output used for operations, such as reading and displaying, but that basically means we need something either coming in or going out. And then we have our rectangles, which is processing, used for arithmetic and data manipulation operations. So these instructions are listed inside the symbol. So then we have our diamonds, which are decisions used for logic or comparison operations. Unlike the input and output processing symbols, which only have one entry and one exit flow line, decision symbols have one entry and two exit paths. And the path chosen depends on whether the answer to the question is yes or no. We have a circle, which is a connector used to join different flow lines. And then we have our little dotted tuning fork, which is an annotation to provide additional information about a flowchart symbol. So if we look at an example of a flowchart, we see we have our start. Then we read in from the user the number of sheets. So the number of sheets is going to be our input. Then we're going to have a processing set, which says set stamps equal to sheets divided by 5. Round stamps up to the wholest number. Then we're going to have another input from the user, or an output to the user rather, that displays the number of stamps. That's the end of our example. Again, we also said that we could use pseudocode, which is going to use English-like phrases with some Visual Basic terms to outline our task. So, our pseudocode example says, determine the proper number of stamps for a letter, read the sheets, set the number of stamps to sheets divided by 5, round the number of stamps up to the whole number, and then display the number of stamps. So notice this is not necessarily Visual Basic code, this is more English, but it's English that's going to be easily translatable into Visual Basic code when we're ready to write our program. The last was a hierarchy chart. So the hierarchy chart shows the different parts of the program and how they relate to each other. So hierarchy charts are also called structure charts, Hippo, top-down chart, VTalk. And as an example here, you can see up at the top we're creating a postal stamp program. The next level down says we're going to read our sheets, we're going to calculate our stamps, we're going to display our stamps. Well, how do we calculate the stamps? Again, we have our stamps, sheets divided by 5, and we want to round it up to the next whole number. So we can also use the divide and conquer method in problem solving. So the divide and conquer method says we take a large problem and we break it into smaller tasks. So we can solve small problems pretty easy, and by solving each one of the small problems and then combining it into a larger problem, we've divided and conquered the entire problem. We have our statement structures, which says sequence, execute instructions from one line to the next without skipping over any lines. We have decisions, which say if the answer to the question is yes, then we want to do one group of instructions, and if the answer is no, then we're going to do a different group of instructions. Or we have looping, which is a series of instructions that are executed repeatedly. You can see, again, the sequence of our flowchart has a start at the top, it goes down to read sheets, it goes down to set the stamps, it goes down to round the stamps up to the next whole number, then it displays the number of stamps, and then it ends. There's no looping in here, there's no decisions that need to be made. It's a straightforward program. If we want to add a decision into our flowchart, you can see now we have a decision matrix. To the left would be our pseudocode. If condition is true, then we process step 1, else process step 2. And you can see from the diamond, you have a yes or no exit. If it's yes, we process step 1. If it's no, we process step 2. Either way, we exit. We also have a looping flowchart. Again, our pseudocode would say do while condition is true, process some steps, loop. We come into our statement, is the condition true? No, we exit. Is the condition true? Yes, then we process some steps and we go back to the beginning. Is the condition true? If it's yes, then we process those steps again until which case it is no, and then we can exit. So we talk about the direction of numbered New York City streets algorithm. So our problem is, given a street in New York of a one-way street, we want to decide if the direction of the street is eastbound or westbound. So in New York City, even-numbered streets are eastbound, odd-numbered streets are westbound. So we have our flowchart. Start, we get the street. Is the street even? No, then it's westbound. Is the street even? Yes, then it's eastbound. Either way, we come to the end of our program. Our pseudocode says, determine the direction of a numbered street, get the street. If it's even, then display eastbound, else display westbound. Because we know if it's not eastbound, then it has to be westbound. So we don't need to test that for an if. Our hierarchy chart says we're talking about our street direction program. We're going to get our street number. We're going to decide whether or not the street is numbered odd or even. And then we're going to display the direction. Another problem we could talk about would be a class average algorithm. So our problem is to calculate and report the average grade for the class. So we want the average grade equal to the sum of all the grades divided by the number of students. And our input, of course, is going to be the student grades. Our processing is going to be finding the sum of all grades, counting the number of students, and then calculating the average. And the output is going to be the average grade. So if we look at our flowchart, we have a start. We initialize the counter and sum equal to 0. So when we start out, we're going to have 0 for our sum and 0 students. Then our program is going to say, is there more students to enter? No. We set our average equal to sum divided by counter, display our average, and end. If there are more students, then we're going to get the grade. We're going to increment our counter, so we've got one more grade. We're going to add the grade to the sum, so our sum's going to increase. And then we're going to ask again if there's more data. So each time we go through the loop, we're incrementing the number of students, and we're also increasing the sum by the value of grade. Until which point there's no more data to enter in, then we're going to set our average to sum divided by counter, display the average, and end. Note, if you were to run this program the first time, and you say, no, there's no more data, it's going to have 0 divided by 0 and result in an error for your program. Again, if we're going to talk pseudocode, we're going to determine the average grade of a class. We're going to initialize our counter and sum to 0, do while there's more data, get the grade, add the grade to the sum, increment the counter, and loop. Loop brings us back to our do statement. While there's more data, get the grade, add the grade to the sum, increase the counter. Once we have all the grades that we're going to enter, our average is our sum divided by counter, we're going to display our average. If we look at it in a hierarchy chart, we have our class average problem, which is going to consist of getting the grade, computing the sum and the number of grades, calculating the average, and displaying the average. So when we're tracing a flowchart, we want to begin at the start symbol and then go all the way to the end symbol. When we're testing an algorithm at the flowchart stage, this is known as desk checking. We haven't actually written the program, we haven't actually coded anything, we're just checking it to make sure it's doing what we expect it to do before we put it into our programming language. Flowcharts, pseudocode, hierarchy charts are program planning tools that are independent of the language being used. So you can take these ideas, you can bring them into C++, you can bring them into Java, you can bring them into Python, and they'll work just as well for you. So for some tips and tricks of flowcharts, flowcharts are very time-consuming to write and difficult to update. So most professional programs are more likely to favor pseudocode and hierarchy charts than flowcharts. But flowcharts are very clearly illustrate the logic of the program, so they're a valuable tool when you're first learning how to program. So that concludes Chapter 1. give the go. Again, you'll find all of the programs that you need to complete for the assignments on CM Connect, and we'll see you at Chapter 2.